going. We're going to start by discussing Cartesian products. It's something all of you are familiar with. You've done this before, right? So let A and maybe not with sets A and B, okay? But you've done it with sets real numbers and real numbers. Okay? You've done that in your calculus classes. But we're using essentially the same definition. The Cartesian product of A and B is the set, it's written A cross B, and the things that are in it are called ordered pairs, okay? Now again, you've seen these, and this should remind you of graphing and all that sort of thing, right? But it's an ordered pair, something there and something there, okay? And the order matters, right? That's why it's called an ordered pair, and you know that again from calculus. And the order matters also in the sense that x has to be an element of A and y has to be an element of B. Okay, so that's our definition, and this is the way mathematics goes. I mean, we haven't really gotten, a whole lot of new definitions, but when we define something, what we try to do is sometimes we introduce new notation, right? And often we introduce new definitions, which should only use things that we already understand. Well, maybe you don't completely understand them always yet when you get the new definition, but hopefully you do. But already things that we have define, or which are our undefined things like ands and element sets and all that, okay? And then so we just build this up. We add new definitions when we need them, and then we prove theorems about those new definitions, and then we discover, oh, I need another definition because I want to understand this, and then you prove new theorems about it, and then you get things like calculus, right, where you define, say, continuous function. We won't get that far in here, but that's an important concept, right? There are a lot of reasons to want to work with continuous functions. A lot of reasons to want to work with differentiable functions. Okay? We're doing the same thing here, except the definitions are a lot more basic, right? And you may not see clearly why we want to do these things yet, but you do know that you've dealt with these kinds of things before, so they at least should be familiar. Actually, the familiarity can be bad sometimes, right? Sometimes when you're familiar with it, you think carelessly about it. And that's something that will give you some trouble a little bit later, okay? So you have to start thinking much more precisely about even things that are familiar to you. All right, so there's the definition. Not a whole lot to it. You may, when you see something like this, your first impulse may to think of this as being like times, okay? Because it looks like an X, right? And so on. But you shouldn't read anything into notation ever, okay? Any properties that we have are either part of the definition or they are proved as theorems, okay? So, for example, what about this? True or not? No. I mean, that's the whole point of an ordered pair, right? There is a situation in which it's true, right? When is that? Yeah, if these are the same set, well then of course, yeah, right. I mean, it's going to be equal. A cross A is going to be equal to A cross A, okay? And so, but this is in general not true. In fact, they're totally unrelated in general because this could be some totally different set from the other one. They could have nothing in common. Okay, and it doesn't even really, I mean, you can start talking about, associative laws and all that, and, there's some things involving that you hit when you get into calculus, of course, because you talk about Rn, right, Euclidean spaces and so on, but we won't get into any of that. So just be careful not to read anything into notation that's not given in the definition or proved as part of the theorem. Okay, so let's go ahead and prove something about this. And the proofs here are going to be fairly straightforward. Why? Because all you've got to work with is that. Yes?
Can you go back one statement? Never read anything into notation.
Yes.
Give me an example.
Wait. I didn't stop at that point. I said, never read anything into notation unless it's a part of your definition or it's a theorem that you've proved about that notation. Okay, I mean the notation is extremely important, right? But don't, think, oh, I see an X and X is usually a commutative operation between things. No, in this case it's not. It's something totally different. Problem is we only got finitely many symbols we can use, right? And sometimes you'll see different kinds of X's and things happening, okay? But we got to use what we got, okay? In the same way that you have to use F for this function, later use F for a different function, you just have to keep it all straight. And what matters is the context, okay? When you see this X and that's a set and that's a set, this means ordered pairs. If you see an X and that's a 3 and that's a 4, then you know it's 12, okay? And that's just the way it has to be, right? We can't produce new letters and symbols all the time. Okay, so let's prove something about this. If, let's say B is a subset of C, then A cross B is a subset of A cross C. Okay, now, again, it's really important to use your notation. So let's think about this for a second. What are we trying to do here? We're trying to prove that this thing, and again, just forget about what it looks like initially, right? You've got to frame this in terms of the general idea, what is it I'm proving? What's the general thing I'm doing? I'm proving that this thing is contained in that thing, okay? Now you all know by now what the opening line is for that, right? If I'm proving something is contained in something else, you now have it framed in your mind what you're supposed to do. So what's your opening line? Okay, go ahead. Okay, A cross B if you want for short, okay? Okay, now, that's fine, except we're now going to have to say something further, okay? So let's just keep going, all right? So let's go back. Now all we have is the definition, so let's go back and look at the definition. And what is the definition telling us? Yeah, this is a set of ordered pairs.
Yeah.
Okay, so if we're going to do this way and just sort of not think ahead and just do the opening line, then we would say, well, this means X equals
some ordered pair A, B.
Yeah, you better change the letters, okay, right? A, B, such that A is an element of A and B is an element of B. Okay, now that's a little bit convoluted, okay? And this looks totally weird, but it's correct, right? Because elements of sets are just elements, right? And you're saying, well, this actually thing looks like AB. However, it is weird to read, and it's a little extra work, and so I would highly encourage you to just start by calling this what it is. Okay, so I would just say, well, okay, let's do this a little bit better and say, I'm trying to show this is contained in that, so when I do my let statement, instead of saying let X be in there and then having to sort through all that, just think ahead a little bit and say, okay, this is an ordered pair. So let's pick it up as an ordered pair from the start. Okay, so I'm going to say instead, let A, B be an element of A cross B. Okay, there's nothing wrong with this mathematically speaking. It's just confusing and it's a little extra work. Right? So a little thought ahead helps it look a little more clear by just calling this thing what it is. It's an ordered pair. And now we can continue kind of like what we did there, except we skipped all that beginning stuff. Now we go back and say, well, we look at our definition. And by the way, by the time you wake up tomorrow morning, you better know this definition, okay? It's true of every definition we get. You better know it by the next morning, okay? That's okay. So then, what do I say now?
A is an element of A, B is an element.
Yes, and there's an and there, right? Okay, now what am I? Let's go look at the end game here, where it's supposed to go. What am I showing about this ordered pair? You want to show that it's in here. So think backwards. Showing it it's here means that A is where? In A, and B is where? In C. Now I only have one piece of information left to use, and that's my hypothesis. So what do I say next?
Since B is a subset of C,
Since B is a subset of C, exactly.
lowercase b must be in C.
Little b is an element of C.
Since A is in A and B is in C, AB is in A cross C.
Yes, okay? So since A is an element of A and B is an element of C, that's what we needed for the ordered pair to be in here. So A comma B is an element of A cross C, and I'm done. Okay? And by the way, I mean, there's always this question, it'll become more and more important as we go along. How many details do I put in there? Should I go back and say, now at this point, when you, not me, you, okay, should you go back and say, well, therefore, you know, A cross B is contained in A cross C? Well, let's have a little talk. I'll have this talk with you periodically, okay? What you're doing in here is you're not trying to convince me that the statement is true. I know the statement is true. I proved it in front of classes, you know, a dozen times, okay? That's not what your goal is. Your goal is to convince me that you know what you're doing. Okay? So, and believe it or not, that's a lot easier than you think it is, or it's easier for me to tell that than you may think it is, okay? So to me, a very confident but brief and correct proof that hits all the right things is great, okay? If you put in that extra line at the end, that's great too, right? And you'll get a feel for this, right? And, you know, some of you may go on to be graduate students in mathematics, okay? And at that point, you know, I'd be willing to take an awful lot less in terms of details from you, right? Because I know that you're proving more complicated things and you start writing down all those details and it gets long and boring, okay? You know, so brevity is good in mathematics as well, but you need to make sure you hit everything. And so what this means, and this sounds awful, and here I am on camera saying it, and that is that I will have different standards for different people. In the sense that if you are writing proofs that are correct, and you want to skip this step here, and you know, because it's very clear, and everything is correct and well stated, then I'll accept that. If you're running in circles in your proof and making a lot of mistakes in other proofs, and you skip that same step, I'm going to think, does this person really know that they skipped a step there? Okay, so your goal should be to work towards doing things very well and very carefully so that I have confidence in what you're doing, okay? And then you can start, you know, oh, this is obvious, okay? By the way, in this class, the definition of obvious is you can explain it to me in one sentence, okay? So if you can't do that, then it's not obvious, okay? And I'll try hard never to use that word, but I will occasionally slip. Yes?
So when we...
So this is done. This would be a proof that I would like to see on your paper.
Okay.
Okay?
By definition, the first statement, let, defines that a, little a is...
Let just says, hey, I'm going to pick up this thing.
Yeah, but the second line, you already know that from the first line.
There is no first line.
Let it.
I mean, this is the first line.
What? Yeah, the second line, then a.
Yes?
Isn't that already implied from
Well,
the first line?
okay, so what I'm doing here is now using the definition of A cross B. Coming back here and saying, okay, this means, of course, now we have A and B instead of X and Y, but I'm just reading out the definition. That I do expect you to do, right, at this stage. What that means is that A is in A and B is in B. So, and that's got, I mean, otherwise you can't do anything, right? Then you're stuck.
Yeah, right. But when you did the subset, so I guess what I was trying to get at is that when you use the subset symbol there, since B is a subset of C,
Yep, that's my hypothesis.
yeah, you didn't really use the definition of subset as formally as you did the ordered pair.
That's true, because again, this goes back to what I expect from you, right? So as we move forward, we will write down fewer details, or you will anyway, and I will too, actually, for that matter, of things that we already sort of accepted, right? So, I mean, I could say B subset of C means if
Exactly.
X, okay,
That's
right.
what I'm wondering.
Okay, this is exactly why I picked this moment to have the talk, okay, right? Okay, so I wouldn't mind if you wrote that down, and it might be good practice if you're still a little bit shaky on some of these things.
Yeah.
But if I saw this on your paper, I would be, okay, great. And my main point right now is, do you see why this is getting me that? Subset, right? Do you understand this line? And here's the important thing also, this is also part of the talk. What I've done here is I've stated clearly what I'm using, right? I haven't written out all the details and definition of subset and all that, but I said I'm using this and I'm concluding that. That tells me you know what you're talking about. If you took this away and just said, now B is an element of C, I would say, okay, why do you know that? But as soon as you have and this is what, I don't know your name yet, but this is what you said precisely, right? Since B is a subset of C, then that tells me, okay, this person is looking at the hypothesis, drawing this conclusion, good. If that's missing, I'm saying, well, okay, I know why that's true, but does the person who wrote this know why it's true? Because they didn't tell me that they're using this fact. Okay? Yes?
I know you have a schedule to go on, but if
I don't really have a schedule, but
this is what you call a direct proof, because you went directly to
yes,
the,
there's no negating in there, right?
Right, so if we wanted to negate this and turn the if,
we don't. Well, I mean, you could. I mean, every proof can be turned into an indirect proof, okay? And, you know, if you want to practice this thing, that's fine, but we'll have plenty of opportunities to use them when it's, you know, shorter to use them, okay? Yeah. Okay, so now what I want to do, you're going to have a bunch of problems like this that are much more complicated, of course. I always want to let you have more fun at home than I have in here, right? Okay, so, but let me draw the standard picture. Okay, so, and actually the shading disappeared in the text. I don't know why, but I just noticed that it's gone, so I'll do some shading here. Okay, so, and it's better in color as well. Okay, now, things get really worse and worse, right? Because in some sense, you're multiplying, I mean, this is, you know, if you think of these as being, you know, this is sort of twice the dimension if you want that, right? Okay, so you're not going to be able to put a little Venn diagram down here because it gets squashed when you try to do it, the Cartesian product, okay? So again, the pictures never prove anything. All they are is they're a device to help you figure things out and help you understand things, okay? So what I'm going to do is I'm going to draw two sets over here, and that's going to be, and these are all actually inside there, okay? This is just sort of a, okay, so, and let's just call this one A. There's a different one in the book, although as I said, the shading doesn't come out, but you should be able to shade it yourself. And then call this one C and this one D. Okay, so again, these are actually in, say this is a big set X, right? And a big set Y, and the big picture is the set of X cross Y. And what I'm going to do now is draw a few things in here. You're going to have to do this now for some actual sets in R cross R, in the Cartesian plane, like you learned about in calculus, okay? And this will help you with various things. Okay, so let's start with, where is A cross B? Well, it's actually useful to think of this as an intersection. You do have an and in there, right? Right? So where are all the things whose first coordinate is in big A. How would I depict that? Just take this, right, and go straight up. Right? That's all the things whose first coordinate are in big A. Now, where are all the things whose second coordinate is in B? Go across like this. Okay? So where is A cross B? It's all ordered pairs so that you're in this because the second coordinate is in B, and you're in this because the first coordinate is in A. So it is an intersection of those two tubes, if you want to call them that. So this is A cross B right here. Okay?
I have a question.
Yes?
Does it matter that A is on the spot that says Y, and then you're putting it first, and that B is in the spot that says X, and you're putting it second?
So, good point. Okay.
How would you do it if you did it backwards?
Well, the other thing I could have done, and you can have your choice, is I could have changed this and that, and then it actually is X cross Y.
What would you do to try? How would you graphically show B cross A in that picture?
Well,
How do you
okay,
move the
what I would do, so what I would do, since at least my convention is to have these be the first coordinates and those be the second coordinates, I would just do like you do in calculus when you invert a function. I would just flip it about this axis here. Now keep in mind that this is not R and R, right? These could be, you know, a set of 10,000 rabbits, okay? Green rabbits and blue rabbits, or purple rabbits and green rabbits, okay, right? Okay. So this is very crude, right? I mean, this could be n-dimensional Euclidean space, and this could be m-dimensional Euclidean space. You know, if you've had matrix algebra, you know you have to deal with big spaces like that, okay? But you can't draw it realistically, obviously. Okay? So, and let's get rid of this junk now, okay, because it's just cluttering up the picture. What about C cross D? Now it should be a little quicker, right? But you should remember what we did, because in your homework you're going to need to do that with some actual subsets of R cross R. Okay, so now where does C cross D? Well, okay, so we just start here, right? Over. Whoops, too far. There we go.
D cross C?
D cross C, excuse me. I don't know. I'm saying the wrong things today. Okay, that's D cross C. At least I didn't write it yet, right? So, okay. Now, let's do another one. How about, let's do this in blue. How about A cross C? There, to there, to there, to there, to there. It's not just that little spot there, it's the whole thing, right? And how about A cross B intersect D cross C?
Square.
Yeah, it's this little guy right here. Okay, then now we're just thinking of this as a Venn diagram, except the things are square instead of circles, right? So there's A cross B, and there's D cross C right there, and so the intersection is that. Okay? So you're going to have to decide, these are going to be statements prove or disprove, right? And they're going to be various combinations of these. You're going to have to draw a picture and decide whether they're true, and then go from there. Okay? So these are not going to be real easy at first. Hopefully they'll get easier. All right, any questions about Cartesian products? All right. Let's talk about functions. You say, oh yeah, there's something I know about. Okay. Unfortunately, we're going to have to start a little bit weird, okay, but correctly. Again, the goal here when we make a definition is to define it only using things that we have already either not defined but are using, or theorems that we've proved, or other definitions that we've made, okay? And so really this isn't going to be that unfamiliar, because when you have been in school, you learned how to graph functions, right? There's your function, okay? And when you graph a function, what are the things on the graph?
X is a given number along a number line.
But what kind of a thing is it? It's an ordered pair. Oh boy, right? And instead of R and R, we'll call this X and Y, okay, just for starters, okay? So it's an ordered pair. So a function really is a set of ordered pairs. And that's how we're going to define it. And in fact, the ordered pair, so there's X, right? There's Y. But what's another word for Y? Another way to represent it. Yes, that word is maybe a bad. Okay, so really, a function consists of a bunch of ordered pairs. The first thing is some x, and the second thing is some f of x. Now remember, you learned is that, well, it's like a machine that takes a number and produces a number, something like that. Okay, right. But we don't know what a machine is. There's actually a definition of that in computer science. Okay, but we don't, like Turing machine. Okay, but we don't know what that is. So, but we do know what ordered pairs are, right? And we know what sets are, and so we're going to define it in this way. Now, not everything I put up there is a function, right? I mean, what if I, did this, okay, right? I mean, is this now a function? It's still a collection of ordered pairs. I could still say, I could still call that, that's still an ordered pair, right? But this is not a function. You learned ages ago. It's not a function. Why isn't it a function?
Doesn't meet the vertical.
You had the vertical line test. Okay, now I don't know what vertical means, okay? I don't know what line is. Well, we know what a test is, but that's not happening for a while, okay? But let's interpret the vertical line test in terms of our notation, okay? It says, you all recognize, well, that's not supposed to happen, right? Well, what does it mean in terms of ordered pairs if that's happening?
There's multiple f of x's for each x.
Yes, so what we've got here, let's change that back to y, because in this case I really don't have a function, okay? But what I have is I have x, y, and I have x, z, and y is not equal to z. This is what I don't want to happen in order to have a function. Okay, that's our translation of the vertical line test. It doesn't use the words vertical line or test. Okay? So, definition. And by the way, I'm putting this definition up again in this way, writing in this way, because it uses familiar things, and then I'm going to introduce the, not familiar things, things we know about. Then I'm going to introduce the familiar notation in just a minute. Okay? So, let x and y be sets. A function from x to y is a set, and here's where the weirdness starts. I'm going to call the function is going to be called f. Just, I don't want to be too weird on you, right? Okay, the function is going to be called f, but it's a set of ordered pairs. In x cross y, such that, now the first condition describes x as the domain of the function. Okay, so we didn't really talk about that here, but you've heard about the domain of a function, right? In calculus, it was often just where the function is defined, right? Like the square root of x. Its domain is 0, infinity, including 0, right? Because at least if you're talking about a real valued function, you can't define it for negative real numbers, okay? So in this class and in just about all mathematical situations, when you talk about f from x to y, x is supposed to be the whole domain, okay? And so that in our notation means the following. For every, so we want everything in x to go somewhere with this function, all right? That's the intuitive idea. That is, x is the domain. So for every x an element of x, there is some x, y, an element of f. Okay? And again, we're going to use this briefly, and I'm going to force you just because I'm not a nice guy. No, because I'm trying to make you stronger. Okay? I'm going to force you to use this notation in a couple of exercises because it's healthy. All right? We're going to quickly abandon it. All right? But does everybody see that this is describing the domain as being x? That means for every x in big X, there's some ordered pair corresponding to it in this function. Okay, so every x goes in there somehow. Doesn't mean every y in big Y gets hit. We'll talk about that later, okay? But every x is supposed to go into this function. And the number 2 here is going to be our translation of the vertical line test. Now somebody should be able to tell me what it is. It's an if-then statement. So if we want that to not happen, so if we have if x, y, an element of f, and x, z is an element of f, then y equals z. Okay, there's your vertical line test. And that's what ensures that the function is a single valued function. You know, when you get farther along in mathematics, and this comes up even in engineering and science and so on, there are multiple valued functions, but we won't get into that in here. Okay, all our functions are single valued, and this is what ensures it. So this ensures it's single valued. This ensures that it's defined on all of x. So x is called the domain. Of f. Everybody with me? Okay, if my back is turned, you can always yell at me to turn around, okay, if you've got a question. Okay, so we're done with that notation, except as I said for some homework. So we'll use familiar notation. Y equal f of x rather than x, y, an element of f. Okay, so now all I'm doing here is changing notation. An ordered pair, well, this was just the notation that goes back in history for, well, an ordered pair. Okay, there are other ways to represent that. We could have said, that, but the problem with that is it's been used for something else that's radically different. Okay, and also this is useful for stringing them out, right? Now sometimes you'll see ordered pairs like this. That's bad, okay, because that's really the set containing those two, and there the order doesn't matter. Okay, so this is just a notation, and the notation gets the order, right? Because this is the first one, that's the second one. You can't just turn them around, okay? Well, this also captures two things with an order, right? The thing that's in there cannot just be swapped with the thing that's in there. You may remember doing that in calculus. You may have some vague memory of this, right? And when you did that, you were doing what? You were finding inverse functions, and that was, right? This was exactly the question that was asked earlier, okay? But then it's a different function, right? And not all functions have inverses, right? We'll get into that later. Remember a horizontal line test, right? That's when you get an inverse. Okay, who knows what horizontal means? Okay. So, and the one more definition, the range of f is the set of all y such that y equals f of x for some x in element x. Okay, I mean, you think of the range as everything that's hit by this function, but of course if you're trying to prove something, what does hit mean? I don't know what that means, right? This is what you have to use. Okay, so and that's what it means, right? Y is f of x for some x in element of x, that is y comes out of this function for some x that goes in. So you can still use your intuition, you know, but just be careful, right? Just be very careful about it. Okay, so everything is familiar now, but now things are going to get a little bit tricky. We need to have two new definitions. And these will, I guarantee you, give a lot of you a lot of trouble, and you need to just work with it and work with it until it becomes instinctive. Let f from x onto y be a function for any a subset of x. I'm going to define f of a equal to the set of all y in element of y such that y equals f of x for some x in element of a. Okay, I'll talk about that again a little bit more in a minute, but I'll give you some examples. For any b a subset of y, define f inverse of b to be equal to the set of all x in element of a. Sorry. X in element of x such that f of x is an element of b. Okay, just a word of warning. I haven't said anything about the function f. F may not have an inverse, even though we're not talking about it yet. You kind of know what that means, right? But this notation always, this set always exists. It could be empty, but it's a perfectly well-defined set.